The following is a conversation with Lex Smolin. He's a theoretical physicist, co-inventor of loop quantum gravity, and a contributor of many interesting ideas to cosmology, quantum field theory, the foundations of quantum mechanics, theoretical biology, and the philosophy of science. He's the author of several books, including one that critiques the state of physics and string theory called The Trouble with Physics, and his latest book, Einstein's Unfinished Revolution, The Search for What Lies Beyond the Quantum. He's an outspoken personality in the public debates on the nature of our universe among the top minds in the theoretical physics community. This community has its respected academics, its naked emperors, its outcasts and its revolutionaries, its madmen and its dreamers. This is why it's an exciting world to explore through long-form conversation. I recommend you listen back to the episodes with Leonard Susskind, Sean Carroll, Michio Kaku, Max Tegmark, Eric Weinstein, and Jim Gates. You might be asking, why talk to physicists if you're interested in AI? To me, creating artificial intelligence systems requires more than Python and deep learning. It requires that we return to exploring the fundamental nature of the universe and the human mind. Theoretical physicists venture out into the dark, mysterious, psychologically challenging place of first principles more than almost any other discipline. This is the Artificial Intelligence Podcast. If you enjoy it, subscribe on YouTube, give it 5 stars on Apple Podcast, support it on Patreon, or simply connect with me on Twitter at Lex Fridman, spelled Fridman. As usual, I'll do 1 or 2 minutes of ads now and never any ads in the middle that can break the flow of the conversation. I hope that works for you and doesn't hurt the listening experience. This show is presented by Cash App, the #1 finance app in the App Store. When you get it, use code LEXPODCAST. Cash App lets you send money to friends, buy Bitcoin, and invest in the stock market with as little as $1. Since Cash App allows you to buy Bitcoin, let me mention that cryptocurrency in the context of the history of money is fascinating. I recommend A Cent of Money as a great book on this history. Debits and credits on ledgers started around 30,000 years ago. The US dollar, of course, created over 200 years ago. And Bitcoin, the first decentralized cryptocurrency, was released just over 10 years ago. So given that history, cryptocurrency is still very much in its early days of development, but it still is aiming to, and just might, redefine the nature of money. If you get Cash App from the App Store or Google Play and use the code LEXPODCAST, you'll get $10, and Cash App will also donate $10 to FIRST, one of my favorite organizations that is helping to advance robotics and STEM education for young people around the world. And now, here's my conversation with Lex Smolin. What is real? Let's start with an easy question. Put another way, how do we know what is real and what is merely a creation of our human perception and imagination?
We don't know. We don't know. This is science. I presume we're talking about science. And we believe, or I believe, that there is a world that is independent of my existence and my experience about it and my knowledge of it. And this I call the real world.
So you said science, but even bigger than science. What?
Sure. I need not have said this is science. I just was, warming up.
Warming up. Okay, now that we're warmed up, let's take a brief step outside of science. Is it completely a crazy idea to you that everything that exists is merely a creation of our mind? So there's a few, not many, this is outside of science now, people who believe sort of perception is fundamentally what's in our human perception, the visual cortex and so on, the cognitive constructs that's being formed there is the reality. And then anything outside is something that we can never really grasp. Is that a crazy idea to you?
There's a version of that is not crazy at all. What we experience is constructed by our brains, and by our brains in an active mode. So we don't see the raw world. We see a very processed world. We feel something was very processed through our brains, and our brains are incredible. But I still believe that behind that experience, that mirror or veil or whatever you want to call it, there is a real world, and I'm curious about it.
Can we truly, how do we get a sense of that real world? Is it through the tools of physics, from theory to the experiments? Or can we actually grasp it in some intuitive way that's more connected to our ape ancestors? Or is it still fundamentally the tools of math and physics that really allow us to grasp it?
Well, let's talk about what tools they are. What you say are the tools of math and physics. I mean, I think we're in the same position as our ancestors in the caves or before the caves or whatever. We find ourselves in this world and we're curious. We also, it's important to be able to explain what happens when there are fires, when there are not fires, what animals and plants are good to eat, and all that stuff. But we're also just curious. We look up in the sky and we see the sun and the moon and the stars, and we see some of those move, and we're very curious about that. And I think we're just naturally curious. So we make this is my version of how we work. We make up stories and explanations, and there are two things which I think are just true of being human. We make judgments fast because we have to. To survive, is that a tiger or is that not a tiger? Mm-hmm. And we go.
Act.
We have to act fast on incomplete information. So we judge quickly, and we're often wrong, or at least sometimes wrong, which is all I need for this. We're often wrong. So we fool ourselves, and we fool other people readily. And so there's lots of stories that get told, and some of them result in a concrete benefit, and some of them don't. And
so you said we're often wrong, but what does it mean to be right?
Right. So, that's an excellent question. To be right. Well, since I believe that there is a real world, I believe that you can challenge me on this if you're not a realist. A realist is somebody who believes in this real objective world, which is independent of our perception. If I'm a realist, I think that to be right is to come closer. I think, first of all, there's a relative scale. There's not right and wrong. There's right or more right and less right. And you're more right if you come closer to an exact, true description of that real world. Now, can we know that for sure? No.
And the scientific method is ultimately what allows us to get a sense of how close we're getting to that real world?
No, on two counts. First of all, I don't believe there's a scientific method. I was very influenced when I was in graduate school by the writings of Paul Feyerabend, who was an important philosopher of science, who argued that there isn't a scientific method.
There is, or there
is not?
There's not. Can you elaborate? If I'm sorry if you were going to, but can you elaborate on what does it mean for there not to be a scientific method? This notion that I think a lot of people believe in this day and age.
Sure. Paul Feyerabend, he was a student of Popper, who taught Karl Popper, and Feyerabend argued, both by logic and by historical example, that you name anything that should be part of the practice of science. Say you should always make sure that your theories agree with all the data that's already been taken. And he'll prove to you that there have to be times when science contradicts, when some scientist contradicts that advice for science to progress overall. So it's not a simple matter. I think of science as a community and
of people,
and of a community of people bound by certain ethical percepts, whatever that is.
So in that community, a set of ideas they operate under, meaning ethically, of kind of the rules of the game they operate under.
Don't lie, report all your results, whether they agree or don't agree with your hypothesis. Check. the training of a scientist mostly consists of methods of checking, because again, we make lots of mistakes. We're very error prone. But there are tools both on the mathematics side and the experimental side to check and double check and triple check. And a scientist goes through a training, and I think this is part of it. You can't just walk off the street and say, yo, I'm a scientist. You have to go through the training, and the test that lets you be done with the training is, can you form a convincing case for something that your colleagues will not be able to shout down, because they'll ask, did you check this, and did you check that, and did you check this, and what about a seeming contradiction with this? And you've got to have answers to all those things, or you don't get taken seriously. And when you get to the point where you can produce that kind of defense and argument, then they give you a PhD. And you're kind of licensed. You're still going to be questioned, and you still may propose or publish mistakes, but the community is going to have to waste less time fixing your mistakes.
Yes. But if you can maybe linger on it a little longer,
Sure.
What's the gap between the thing that community does and the ideal of the scientific method? The scientific method is, you should be able to repeat an experiment. There's a lot of elements to what construes the scientific method, but the final result, the hope of it, is that you should be able to say with some confidence that a particular thing is close to the truth.
Right, but there's not a simple relationship between experiment and hypothesis or theory. For example, Galileo did this experiment of dropping a ball from the top of a tower, and it falls right at the base of the tower. And an Aristotelian would say, wow, of course it falls right to the base of the tower. That shows that the earth isn't moving while the ball is falling. And Galileo says, no, wait, there's a principle of inertia, and it has an inertia in the direction which the earth isn't moving, and the tower and the ball and the earth all move together. When the principle of inertia tells you it hits the bottom, it does look, therefore my principle of inertia is right. And the Aristotelian says, no, Aristotle's science is right, the earth is stationary. And so you've got to get an interconnected bunch of cases and work hard to line up an explanation. It took centuries to make the transition from Aristotelian physics to the new physics. It wasn't done till Newton in 1687.
So what do you think is the nature of the process that seems to lead to progress? If we at least look at the long arc of science, of all the community of scientists, they seem to do a better job at coming up with ideas that engineers can then take on and build rockets with, or build computers with, or build cool stuff with.
I don't know. A better job than what?
Than this previous century. So century by century, we'll talk about string theory and so on, and kind of possible what you might think of as dead ends and so on.
Which is not the way I think of string theory.
Yeah.
But we'll straighten all. We'll get
straighten
all
it
the
out.
strings
Okay.
straight.
But there is, nevertheless, in science, very often at least temporary dead ends. But if you look
Sure.
at through centuries, the century before Newton and the century after Newton, it seems like a lot of ideas came closer to the truth that then could be usable by our civilization to build the iPhone, right? To build cool things that improve our quality of life. That's the progress I'm kind of referring to.
Can I say that more precisely?
Yes. It's a low bar.
Because I think it's important to get the time places right.
Yes.
There was a scientific revolution that partly succeeded between about 1900 or late 1890s and into the 1930s, 1940s, and maybe some, if you stretched it, into the 1970s. And the technology, this was the discovery of relativity, and that included a lot of developments of electromagnetism. The confirmation, which wasn't really well confirmed into the 20th century, that matter was made of atoms, and the whole picture of nuclei with electrons going around them, this is early 20th century. And then quantum mechanics was from 1905, it took a long time to develop till the late 1920s, and then it was basically in final form. And the basis of this partial revolution, and we can come back to why it's only a partial revolution, is the basis of the technologies that you mentioned. All of, electrical technology was being developed slowly with this, and in fact, there's a close relation between the development of electricity and the electrification of cities in the United States and Europe and so forth, and the development of this science. The fundamental physics since the early 1970s doesn't have a story like that so far. There's not a series of triumphs and progresses, and there's not any practical application.
So just to linger briefly on the early 20th century and the revolutions in science that happened there, what was the method by which the scientific community kept each other in check about when you get something right, when you get something wrong? Is experimental validation ultimately the final test?
It's absolutely necessary. And the key things were all validated. The key predictions of quantum mechanics and of the theory of electricity and magnetism.
So before we talk about Einstein, your new book, before string theory, quantum mechanics, so on, let's take a step back at a higher level question. What is, that you mentioned, what is realism? What is anti-realism? And maybe why do you find realism, as you mentioned, so compelling?
Realism is the belief in an external world independent of our existence, our perception, our belief, our knowledge. A realist, as a physicist, is somebody who believes that there should be possible some completely objective description of each and every process at the fundamental level, which describes and explains exactly what happens and why it happens.
That kind of implies that that system, in a realist view, is deterministic, meaning there's no fuzzy magic going on that you can never get to the bottom of. You can get to the bottom of anything and perfectly describe it.
Some people would say that. I'm not that interested in determinism, but I could live with a fundamental world which had some chance in it.
So do you said you could live with it, but do you think God plays dice in our universe?
I think it's probably much worse than that.
In which direction?
I think that theories can change, and theories can change without warning. I think the future is open. You
mean the fundamental laws of physics can change?
Yeah.
Oh, okay, we'll get there. I thought we would be able to find some solid ground, but apparently,
well, the ground is
the entirety
solid.
of it, well, temporarily so. Probably. Okay, let's. So realism is the idea that while the ground is solid, you can describe it. What's the role of the human being, our beautiful, complex human mind, in realism? Do we have are we just another set of molecules connected together in a clever way, or the observer, does the observer, our human mind, consciousness, have a role in this realism view of the physical universe?
There's two questions you could be asking. Yeah. Does our conscious mind, do our perceptions play a role in making things real, or things becoming? That's question one. Question two is, does this, we can call it a naturalist view of the world, that is based on realism allow a place to understand the existence of and the nature of perceptions and consciousness and mind? And that's question two. Question two, I do think a lot about, and my answer, which is not an answer, is I hope so, but it certainly doesn't yet.
So what
question one, I don't think so. But of course, the answer to question one depends on question two.
Right.
So I'm not up to question one yet.
So question two is the thing that you can kind of struggle with at this time.
Yes.
What about the anti-realists? So what are the different camps of anti-realists that you've talked about? I think it would be nice if you could articulate for the people for whom there is not a very concrete real world, or there's divisions, or it's messier than the realist view of the universe. What are the different camps? What are the different views?
I'm not sure I'm a good scholar and can talk about the different camps and analyze it, but many of the inventors of quantum physics were not realists, were anti-realists. And there are scholars they lived in a very perilous time between the two world wars. And there were a lot of trends in culture which were going that way. But in any case, they said things like, the purpose of science is not to give an objective, realist description of nature as it would be in our absence. This might be, say, Niels Bohr. The purpose of science is as an extension of our conversations with each other to describe our interactions with nature. And we're free to invent and use terms like particle or wave or causality or time or space if they're useful to us and they carry some intuitive implication. But we shouldn't believe that they actually have to do with what nature would be like in our absence, which we have nothing to say about.
Do you find any aspect of that? Because you kind of said that we human beings tell stories. Do you find aspects of that kind of anti-realist view of Niels Bohr compelling? That we're fundamentally are storytellers, and then we create tools of space and time and causality and whatever this fun quantum mechanics stuff is to help us tell the story of our world.
Sure. I just would like to believe that there's an aspiration for the other thing.
The other thing being what? The
realist point of view.
Do you hope that the stories will eventually lead us to discovering the real world as it is?
Yeah.
Is perfection possible, by the way?
No. Well, that's... You mean, will we ever get there and know that we're there?
Exactly.
That's not that's for people 5,000 years in the future. We're certainly nowhere near there yet.
Do you think reality that exists outside of our mind, do you think there's a limit to our cognitive abilities as, again, descendants of apes who are just biological systems? Is there a limit to our mind's capability to actually understand reality? Sort of, there comes a point, even with the help of the tools of physics, that we just cannot grasp some fundamental aspects of that reality.
Again, I think that's a question for 5,000 years in the future.
We're not even close to that limit.
I think there is a universality. Here, I don't agree with David Deutsch about everything, but I admire the way he put things in his last book. And he talked about the role of explanation. And he talked about the universality of certain languages, or the universality of mathematics, or of computing, and so forth. And he believed that the universality, which is something real, which is somehow comes out of the fact that a symbolic system or a mathematical system can refer to itself and can, I forget what that's called, can reference back to itself.
Mm-hmm.
And build, in which he argued for a universality of possibility for our understanding, whatever is out there. But I admire that argument, but it seems to me we're doing okay. so far, but we'll have to see.
Whether there is a limit or not. For now, we got plenty to play with.
Yeah. There are things which are right there in front of us, which we miss. And I'll quote my friend Eric Weinstein in saying, look, Einstein carried his luggage, Freud carried his luggage, Marx carried his luggage, Martha Graham carried her luggage, etc. Edison carried his luggage. All these geniuses carried their luggage. And not once before relatively recently did it occur to anybody to put a wheel on luggage and pull it. And it was right there waiting to be invented for centuries.
So this is Eric Weinstein. Yeah. What do the wheels represent? Are you basically saying that there's stuff right in front of our eyes that once it just clicks, we put the wheels in the luggage, a lot of things will fall into place?
Yes, I do. And every day I wake up and think, why can't I be that guy who was walking through the airport? Yeah.
What do you think it takes to be that guy? Because, like you said, a lot of really smart people carried their luggage.
Mm-hmm.
What, just psychologically speaking, so Eric Weinstein is a good example of a person who thinks outside the box.
Yes.
Who resists almost conventional thinking. You're an example of a person who, by habit, by psychology, by upbringing, I don't know, but resists conventional thinking as well, just by nature.
Thank you. That's a compliment.
That's a compliment? Good. So what do you think it takes to do that? Is that something you were just born with?
I doubt it. Well, from my studying some cases, because I'm curious about that, obviously. And just in a more concrete way, when I started out in physics, because I started a long way from physics, so it took me not a long time, but a lot of work to get to study it and get into it. So I did wonder about that. And so I read the biographies, and in fact, I started with the autobiography of Einstein and Newton and Galileo and all those people. And I think there's a couple of things. Some of it is luck, being in the right place at the right time. Some of it is stubbornness and arrogance, which can easily go wrong.
Yes.
And I know all of these are doorways. If you go through them slightly at the wrong speed or in the wrong angle, they're ways to fail. But if you somehow have the right luck, the right confidence or arrogance, caring, I think Einstein cared to understand nature with a ferocity and a commitment that exceeded other people of his time. So he asked more stubborn questions. He asked deeper questions. I think, and there's a level of ability, and whether ability is born in or can be developed, to the extent to which it can be developed, like any of these things, like musical talent.
So you mentioned ego. What's the role of ego in that process?
Confidence.
But do you, in your own life, have you found yourself walking that nice edge of too much or too little? So being overconfident and therefore leading yourself astray, or not sufficiently confident to throw away the conventional thinking of whatever the theory of the day, of theoretical physics?
I don't know if I mean, I've contributed what I've contributed. Whether if I had had more confidence in something, I would have gotten further. Yeah. I don't know. Certainly I'm sitting here at this moment with very much my own approach to nearly everything. And I'm calm, I'm happy about that. But on the other hand, I know people whose self-confidence vastly exceeds mine, and sometimes I think it's justified, and sometimes I think it's not justified.
Your most recent book, titled Einstein's Unfinished Revolution. So I have to ask, what is Einstein's Unfinished Revolution? And also, how do we finish it?
Well, that's something I've been trying to do my whole life. But Einstein's unfinished revolution is the twin revolutions which invented relativity theory, special and especially general relativity, and quantum theory, which he was the first person to realize in 1905 that there would have to be a radically different theory which somehow realized or resolved the paradox of the duality of particle and wave for photons.
And he was, I mean, people I think don't always associate Einstein with quantum mechanics, because I think his connection with it, founding as a one of the founders, I would say, of quantum mechanics, he kind of put it in the closet. Is it?
Well, he didn't believe that the quantum mechanics as it was developed in the late 1920s was completely correct. At first, he didn't believe it at all. Then he was convinced that it's consistent but incomplete, and that also is my view. It needs, for various reasons I can elucidate, to have additional degrees of freedom, particles, forces, something to reach the stage where it gives a complete description of each phenomenon, as I was saying, realism demands.
So what aspect of quantum mechanics bothers you and Einstein the most? Is it some aspect of the wave function collapse discussions, the measurement problem? Is it the
measurement problem? I'm not going to speak for Einstein, but the measurement problem, basically, and the fact that...
What is the measurement problem? Sorry.
The basic formulation of quantum mechanics gives you two ways to evolve situations in time. One of them is explicitly when no observer is observing or no measurement is taking place. And the other is when a measurement or an observation is taking place. And they basically contradict each other. But there's another reason why the revolution was incomplete, which is we don't understand the relationship between these two parts. General relativity, which became our best theory of space and time and gravitation and cosmology, and quantum theory.
So for the most part, general relativity describes big things, quantum theory describes little things, and that's the revolution
right.
That we found really powerful tools to describe big things and little things, and it's unfinished because we have two totally separate things, and we need to figure out how to connect them so it can describe everything.
Right, and we either do that, if we believe quantum mechanics as understood now is correct, by bringing general relativity or some extension of general relativity that describes gravity and so forth into the quantum domain. That's called quantize the theory of gravity. Or if you believe with Einstein that quantum mechanics needs to be completed, and this is my view, then part of the job of finding the right completion or extension of quantum mechanics would be one that incorporated space-time and gravity.
So, where do we begin? So, first, let me ask, perhaps you can give me a chance, if I could ask you some just really basic questions. Well, they're not at all. The basic questions are the hardest, but you mentioned space-time. What is space-time?
Space-time, you talked about a construction. So I believe that space-time is an intellectual construction that we make of the events in the universe. I believe the events are real, and the relationships between the events, which cause which, are real. But the idea that there's a four-dimensional smooth geometry which has a metric and a connection and satisfies the equations that Einstein wrote, it's a good description to some scale. It's a good approximation. It captures some of what's really going on in nature. But I don't believe it for a minute is fundamental.
So, okay, we're going to allow me to linger on that. So the universe has events.
Yeah.
Events cause other events.
Yeah.
This is the idea of causality. Okay, yeah. So that's real.
That's in my...
In your view, is real.
Or hypothesis, or the theories that I have been working to develop make that assumption.
Yes. So space-time, you said four-dimensional. Space is kind of the location of things, and time is whatever the heck time is. And you're saying that space-time is both space and time are emergent and not fundamental?
No.
First, sorry, before you correct me, what does it mean to be fundamental or emergent?
Fundamental means it's part of the description as far down as you go. We have this
real.
notion. Yes.
As real it could be.
Yeah. So I think that time is fundamental, and quote goes all the way down, and space does not.
Right.
And the combination of them we use in general relativity that we call space-time also does not.
But what is time then?
I think that time, the activity of time, is the continual creation of events from existing events.
So if there's no events, there's no
nothing.
Time.
Then there's not only no time, there's no nothing.
So
I believe the universe has a history which goes to the past. I believe the future does not exist. There's a notion of a present and a notion of the past. And the past is a story about events that took place to our past.
So you said the future doesn't exist.
Yes.
Could you say that again? Can you try to give me a chance to understand that one more time? So what the events cause other events. What is this universe? Because we'll talk about locality and non-locality.
Good.
Because it's it's not crazy. It's a beautiful set of ideas that you propose. But and if causality is fundamental, I'd just like to understand it better. What is the past? What is the future? What is the flow of time, even the error of time in our universe, in your view? And maybe what's an event, right?
Oh, an event is where something changes, or where it's hard to say because it's a primitive concept. An event is a moment of time within space. This is the view in general relativity, where two particles intersect in their paths, or something changes in the path of a particle. Now, we are postulating that there is, at the fundamental level, a notion, which is an elementary notion, so it doesn't have a definition in terms of other things, but it is something elementary happening.
And it doesn't have a connection to energy or matter or exchange of any.
It does have a connection to energy and matter.
So it's at that level.
Yes, it involves, and that's why the version of a theory of events that I've developed with Marina Cortez. And it's, by the way, I want to mention my collaborators because they've been at least as important in this work as I have. It's Marina Cortez in all the work since about 2013, 2012, 2013 about causality, causal sets. And in the period before that, Roberto Manguibera-Unger, who is a philosopher and a professor of law.
And that's in your efforts together with your collaborators to finish the unfinished revolution. So
yes.
And focused on causality as a fundamental,
yes,
as fundamental to physics. So,
and there's certainly other people we've worked with, but those two people's thinking had a huge influence on my own thinking.
So, in the way you describe causality, that's what you mean of time being fundamental. That causality is fundamental.
Yes.
And what does it mean for space to not be fundamental, to be emergent?
That's very good. That there's a level of description in which there are events create other events, but there's no space. They don't live in space. They have an order in which they caused each other. And that is part of the nature of time for us. So, but there is an emergent approximate description, and you asked me to define emergent, I didn't. An emergent property is a property that arises at some level of complexity larger than and more complex than the fundamental level, which requires some property to describe it, which is not directly explicable or derivable is the word I want, from the properties of the fundamental things.
And space is one of those things. In a sufficiently complex universe, space, three-dimensional position of things emerged.
Yes, and we saw how this happens in detail in some models, both computationally and analytically.
Okay, so connected to space is the idea of locality.
Yes.
So we talked about realism. So I live in this world that like sports. Locality is a thing that, you can affect things close to you and don't have an effect on things that are far away.
Mm-hmm.
It's the thing that bothers me about gravity in general, or action at a distance. Mm-hmm. Same thing that probably bothered Newton, or at least he said a little bit about it. So what do you think about locality? Is it just a construct? Is it us humans just like this idea and are connected to it because we exist in it, we need it for our survival, but it's not fundamental? I mean, it seems crazy for it not to be a fundamental aspect of our reality.
It does.
And so can you comfort me on a sort of as a therapist? How do I?
I'm not a good therapist, but I'll do my best.
Okay.
There are several different definitions of locality when you come to talk about locality in physics. In quantum field theory, which is a mixture of special relativity and quantum mechanics, there is a precise definition of locality. Field operators corresponding to events in space-time which are space-like separated commute with each other as operators.
So in quantum mechanics, you think about the nature of reality as fields, and things that are close in a field have an impact on each other more than farther away.
Yes.
That's very comforting. That makes sense.
So that's a property of quantum field theory, and it's well tested. Unfortunately, there's another definition of local, which was expressed by Einstein and expressed more precisely by John Bell, which has been tested experimentally and found to fail. And this setup is you take two particles. So one thing that's really weird about quantum mechanics is a property called entanglement. Mm-hmm. You can have two particles interact and then share a property without it being a property of either one of the two particles. And if you take such a system and then you make a measurement on particle A, which is over here on my right side, and particle B, which is over here, and somebody else makes a measurement of particle B, you can ask that whatever is the real reality of particle B, it not be affected by the choice the observer at particle A makes about what to measure, not the outcome, just the choice of the different things they might measure. And that's a notion of locality because it assumes that these things are very far space-like separated, and it's going to take a while for any information about the choice made by the people here at A to affect the reality at B. But you make that assumption, that's called Bell locality. Mm-hmm. And you derive a certain inequality that some correlations, functions of correlations have to satisfy. And then you can test that pretty directly in experiments which create pairs of photons or other particles. And it's wrong by many sigma.
In experiment, it doesn't match. So what does that mean?
That means that definition of locality I stated is false.
The one that Einstein was playing with.
Yeah, and the one that I stated, that is, it's not true that whatever is real about particle B is unaffected by the choice that the observer makes as to what to measure in particle A, no matter how long they've been propagating at almost the speed of light or the speed of light away from each other.
No matter? So like the distance between them?
Well, it's been tested, of course. If you want to have hope for quantum mechanics being incomplete or wrong and corrected by something that changes this, it's been tested over a number of kilometers. I don't remember whether it's 25 kilometers or 100 and something kilometers. But
so, in trying to solve the unsolved revolution, in trying to come up with a theory for everything, is causality fundamental and breaking away from locality
absolutely
a crucial step?
Yeah.
So in your book, essentially, those are the two things we really need to think about as a community. So especially the physics community has to think about this. So I guess my question is, how do we how do we finish the unfinished revolution?
Well, I can only tell you what I'm trying to do and what I have abandoned.
Yes,
exactly. As not working.
As one smart ant in an ant colony. Yep.
Or maybe dumb, that's why. Who knows? But anyway, my view of we've had some nice theories invented. Yes. There's a bunch of different ones, both related to quantum mechanics and related to quantum gravity. There's a lot to admire in many of these different approaches, but to my understanding, none of them completely solve the problems that I care about. And so we're in a situation which is either terrifying for a student or full of opportunity for the right student, in which we've got more than a dozen attempts. And I don't think anybody anticipated it would work out this way, which work partly, and then at some point they have an issue that nobody can figure out how to go around or how to solve. And that's the situation we're in. My reaction to that is twofold. One of them is to try to bring people. We evolved into this unfortunate sociological situation in which there are communities around some of these approaches. And to borrow again a metaphor from Eric, they sit on top of hills in the landscape of theories and throw rocks at each other. And as Eric says, we need two things. We need people to get off their hills and come down into the valleys and party and talk and become friendly and learn to say not no but yes and. Yes, your idea goes this far, but maybe if we put it together with my idea, we can go further.
Yes. So in that spirit, I've talked several times with Sean Carroll, who's also written an excellent book recently, and he plays around, is a big fan of the many worlds interpretation of quantum mechanics. So I'm a troublemaker, so let me ask, what's your sense of Sean and the idea of many worlds interpretation? I've read the commentary back and forth. You guys are friendly, respect each other, but have a lot of fun debating.
I love Sean, and he's articulate, and he's a great representative or ambassador of science to the public and for different fields of science to each other. He also, like I do, takes philosophy seriously. And unlike what I do in all cases, he has really done the homework. He's read a lot. He knows the people. He talks to them. He exposes his arguments to them. And there's this mysterious thing that we so often end up on the opposite sides of these issues.
It's fun, though.
It's fun, and I'd love to have a conversation about that, but I would want to include him.
I see. About many worlds. Well,
no, I can tell you what I think about many worlds.
I'd love to, but actually on that, let me pause. Sean has a podcast. You should definitely figure out how to talk to Sean. I actually told Sean I would love to hear you guys just going back and forth. So I hope you can make that happen eventually, you and Sean.
I won't tell you what it is, but there's something that Sean said to me in June of 2016 that changed my whole approach to a problem. But I have to tell him first.
Yes, and that'll be great to tell him on his podcast. So
I can't invite myself to his podcast.
I told him, yeah, okay, we'll make it happen. So many worlds.
Anyway,
what's your view? Many worlds. We talk about non-locality. Many worlds is also a very uncomfortable idea, or beautiful, depending on your perspective. It's very nice in terms of. I mean, there's a realist aspect to it. I think you called it magical realism.
Yes.
just a beautiful line, but at the same time, it's very difficult for our limited human minds to comprehend. So, what are your thoughts about it?
Let me start with the easy and obvious and then go to the scientific.
Okay.
It doesn't appeal to me. It doesn't answer the questions that I want answered. And it does so to such a strong case that when Roberto Manguiber-Unger and I began looking for principles, and I want to come back and talk about the use of principles in science, because that's the other thing I was going to say, and I don't want to lose that. When we started looking for principles, we made our first principle: there is just one world, and it happens once. But so it's not helpful to my personal approach, to my personal agenda. But of course, I'm part of a community. And my sense of the many worlds interpretation, I have thought a lot about it and struggled a lot with it, is the following. First of all, there's Everett himself. There's what's in Everett. And there are several issues there connected with the derivation of the Born rule, which is the rule that gives probabilities to events. And the reasons why there is a problem with probability is that I mentioned the two ways that physical systems can evolve. The many worlds interpretation cuts off one, the one having to do with measurement, and just has the other one, the Schrodinger evolution, which is the smooth evolution of the quantum state. But the notion of probability is only in the second rule, which we've thrown away. So where does probability come from? And you have to answer the question, because experimentalists use probabilities to check the theory. Now, at first sight, you get very confused because there seems to be a real problem, because in the many worlds interpretation, this talk about branches is not quite precise, but I'll use it. There's a branch in which everything that might happen does happen, with probability 1 in that branch. You might think you could count the number of branches in which things do and don't happen, and get numbers that you can define as something like frequentist probabilities. And Everett did have an argument in that direction. But the argument gets very subtle when there are an infinite number of possibilities, as is the case in most quantum systems. And my understanding, although I'm not as much of an expert as some other people, is that Everett's own proposal failed, did not work. There are then, but it doesn't stop there. There is an important idea that Everett didn't know about, which is decoherence, and it is a phenomenon that might be very much relevant. And so a number of people post-Everett have tried to make versions of what you might call many worlds quantum mechanics. And this is a big area, and it's subtle, and it's not the kind of thing that I do well. So I consulted. That's why there's 2 chapters on this in the book I wrote. Chapter 10, which is about Everett's version, and Chapter 11. There's a very good group of philosophers of physics in Oxford. Simon Saunders, David Wallace, Harvey Brown, and a number of others. And of course, there's David Deutsch, who is there. And those people have developed and put a lot of work into a very sophisticated set of ideas designed to come back and answer that question. They have the flavor of, there are really no probabilities, we admit that. But imagine if the Everett story was true and you were living in that multiverse, how would you make bets? And so they use decision theory from the theory of probability and gambling and so forth to shape a story of how you would bet if you were inside an Everettian universe and you knew that. And there's a debate among those experts as to whether they or somebody else has really succeeded. And when I checked in as I was finishing the book with some of those people, like Simon, who's a good friend of mine, and David Wallace, they told me that they weren't sure that any of them was yet correct. So that's what I put in my book. Now, to add to that, Sean has his own approach to that problem in what's called self-referencing or self-locating observers. And it doesn't, I tried to read it and it didn't make sense to me, but I didn't study it hard. I didn't communicate with Sean. I didn't do the things that I would do. So I had nothing to say about it in the book.
Yeah.
I don't know whether it's right or not.
Let's talk a little bit about science. You mentioned the use of principles in science. What does it mean to have a principle, and why is that important?
When I feel very frustrated about quantum gravity, I like to go back and read history. And of course, Einstein and his achievements are a huge lesson and hopefully something like a role model. And it's very clear that Einstein thought that the first job when you want to enter a new domain of theoretical physics is to discover and invent principles, and then make models of how those principles might be applied in some experimental situation, which is where the mathematics comes in. So for Einstein, there was no unified space and time. Minkowski invented this idea of space-time. For Einstein, it was a model of his principles or his postulates. And I've taken the view that we don't know the principles of quantum gravity. I can think about candidates, and I have some papers where I discuss different candidates, and I'm happy to discuss them. But my belief now is that those partially successful approaches are all models which might describe indeed some quantum gravity physics in some domain, in some aspect, but ultimately would be important because they model the principles, and the first job is to tie down those principles. So that's the approach that I'm taking.
So speaking of principles, in your 2006 book, The Trouble with Physics, you criticized a bit string theory for taking us away from the rigors of the scientific method, or whatever you would call it. But what's the trouble with physics today, and how do we fix it?
Can I say how I read that book?
Sure.
Because I'm not, this of course has to be my fault, because you can't as an author claim after all the work you put in that you are misread. But I will say that many of the reviewers who were not personally involved, and even many who were working on string theory or some other approach to quantum gravity, communicated with me and told me they thought that I was fair. And balance was the word that was usually used. So let me tell you what my purpose was in writing that book, which clearly got diverted because there was already a rather hot argument going on. And this is...
On which topic? On string theory specifically? Or in general in physics?
No, more specifically than string theory. So, since we're in Cambridge, can I say that? We're doing this in Cambridge?
Yeah, of course. Cambridge, just to be clear, Massachusetts, and on Harvard campus.
Right. So Andy Strominger is a good friend of mine and has been for many, many years. And Andy, so originally there was this beautiful idea that there were 5 string theories, and maybe they would be unified into one. And we would discover a way to break the symmetries of one of those string theories and discover the standard model and predict all the properties of the standard model particles, like their masses and charges and so forth, coupling constants. And then there was a bunch of solutions to string theory found, which led each of them to a different version of particle physics with a different phenomenology. These are called the Calabi-Yau manifolds, named after Yau, who was also here. Certainly we've been friends at some time in the past anyway. And then there were, nobody was sure, but hundreds of thousands of different versions of string theory. And then Andy found there was a way to put a certain kind of mathematical curvature called torsion into the solutions. And he wrote a paper, String Theory with Torsion, in which he discovered there was not formally uncountable, but he was unable to invent any way to count the number of solutions or classify the diverse solutions. And he wrote that this is worrying because doing phenomenology the old-fashioned way by solving the theory is not going to work because there's going to be loads of solutions for any proposed phenomenology for anything the experiments discovered. Now, it hasn't quite worked out that way. But nonetheless, he took that worry to me. We spoke at least once, maybe 2 or 3 times about that. And I got seriously worried about that. And this is just a little...
It's almost like an anecdote that inspired your worry about string theory in general?
Well, I tried to solve the problem. And I tried to solve the problem. I was reading at that time a lot of biology, a lot of evolutionary theory, like Lynn Margulis and Steve Gould and so forth. And I could take your time to go through the things, but it occurred to me maybe physics was like evolutionary biology, and maybe the laws evolved, and there was, the biologists talk about a landscape, a fitness landscape of DNA sequences or protein sequences or species or something like that. And I took their concept and the word landscape from theoretical biology and made a scenario about how the universe as a whole could evolve to discover the parameters of the standard model. And I'm happy to discuss, that's called cosmological natural selection.
Cosmological natural selection.
Yeah, and I
wow. So the parameters of the standard model. So it's the laws of physics are changing. This idea would say that the laws of physics are changing in some way that echoes that of natural selection, or just it adjusts in some way towards some goal.
Yes, and I published that. I wrote the paper in 88 or 89. The paper was published in 92. My first book in 1997, The Life of the Cosmos, was explicitly about that. And I was very clear that what was important is that because you would develop an ensemble of universes, but they were related by descent through natural selection, almost every universe would share the property that its fitness was maximized to some extent, or at least close to maximal. And I could deduce predictions that could be tested from that. And I worked all of that out, and I compared it to the anthropic principle where you weren't able to make tests or make falsifications. All of this was in the late 80s and early 90s.
So that's a really compelling notion, but how does that help you arrive?
I'm coming to where the book came from.
Yes.
So what got me, I worked on string theory. I also worked on loop quantum gravity, and I was one of the inventors of loop quantum gravity. And because of my strong belief in some other principles, which led to this notion of wanting a quantum theory of gravity to be what we call relational or background independent, I tried very hard to make string theory background independent, and ended up developing a bunch of tools which then could apply directly to general relativity, and that became loop quantum gravity. So the things were very closely related and have always been very closely related in my mind. The idea that there were two communities, one devoted to strings and one devoted to loops, is nuts and has always been nuts.
Okay, so
So anyway,
there's this nuts community of loops and strings that are all beautiful and compelling and mathematically speaking. And what's the trouble with all that? Why is that? Why is that such a problem?
so I was interested in developing that notion of how science works based on a community and ethics that I told you about.
Yes.
And I wrote a draft of a book about that, which had several chapters on methodology of science, and it was a rather academically oriented book. And those chapters were the first part of the book, the first third of it, and you can find their remnants in what's now the last part of The Trouble with Physics. And then I described a number of test cases, case studies, and one of them, which I knew, was the search for quantum gravity and string theory and so forth. And I was unable to get that book published. So somebody made the suggestion of flipping it around and starting with the story of string theory, which was already controversial. This was 2004, 2005. But I was very careful to be detailed, to criticize papers and not people. You won't find me criticizing individuals. You'll find me criticizing certain writing. But in any case, here's what I regret. Let me make your program worthwhile.
Yes.
As far as I know, with the exception of not understanding how large the applications to condensed matter, say, of ADS-CFT would get, I think largely my diagnosis of string theory, as it was then, has stood up since 2006. What I regret is that the same critique, I was using string theory as an example, and the same critique applies to many other communities in science I know of, including, and this is what I regret, my own community, that is a community of people working on quantum gravity outside string theory. And I considered saying that explicitly. But to say that explicitly, since it's a small, intimate community, I would be telling stories and naming names and making a kind of history that I have no right to write. So I stayed away from that, but was misunderstood.
But if I may ask, is there a hopeful message for theoretical physics that we can take from that book, sort of that looks at the community, not just your own work on now with causality and non-locality, but just broadly in understanding the fundamental nature of our reality? What's your hope for the 21st century in physics that we can take?
That we solve the problem.
That we solve the unfinished problem of Einstein's.
So that's certainly the thing that I care about most and hope for most. So let me say one thing. Among the young people that I work with, I hear very often and sense a total disinterest in these arguments that we older scientists have, and an interest in what each other is doing. And this is starting to appear in conferences where the young people interested in quantum gravity make a conference and they invite loops and strings and causal dynamical triangulations and causal set people. And we're having a conference like this next week, a small workshop at Perimeter, and I guess I'm advertising this. And then in the summer, we're having a big full-on conference, which is just quantum gravity. It's not strings, it's not loops. But the organizers and the speakers will be from all the different communities.
Yes.
And this, to me, is very helpful.
That the different ideas are coming together.
At least people are expressing an interest in that.
It's a huge honor talking to you, Lee. Thanks so much for your time today.
Thank you.
Thanks for listening to this conversation, and thank you to our presenting sponsor, Cash App. Download it, use code Lex Podcast. You'll get $10, and $10 will go to FIRST, an organization that inspires and educates young minds to become science and technology innovators of tomorrow. If you enjoy this podcast, subscribe on YouTube, give it 5 stars on Apple Podcast, follow on Spotify, support it on Patreon, or simply connect with me on Twitter at Lex Fridman. And now, let me leave you with some words from Lex Smolin. One possibility is God is nothing but the power of the universe to organize itself. Thanks for listening, and hope to see you next time.